Okay, so we just did quiz 2. You've got a pretty lengthy homework assignment due on Tuesday, so I'd invite you to stop by my office hours if you've got any questions that pop up, and I'll try to remember to take the key to that assignment home over the weekend in case you've got any questions that can't wait until Monday, and that's fine. I don't mind answering your questions, although sometimes it's a challenge to write. Some things are more visual, but I'll do my best. We're going to be talking about rotational flow today, and here on the board I've reconstructed a table that I've shown you previously, because today we finish this table. We're talking about one other type of acceleration that we haven't discussed in detail before. That's centripetal acceleration. And just like each of these other acceleration types are associated with a certain flow type, where convective acceleration went with non-uniform flow, local acceleration is associated with unsteady flow, meaning a change with respect to time. Centripetal acceleration and rotational flow are having to do with the change in velocity with respect to position. Well, convective flow is also, convective acceleration also has to do with change in velocity with respect to position, but velocity is a vector, meaning it has two components, direction and magnitude. Convective acceleration is focusing on the change in velocity magnitude part, and today what we're going to be focusing on is a change in velocity, meaning the change in direction. And here are the equations that describe changes in pressure for each of them. Okay, so we've just gone through that on the whiteboard there. I'd like to show you a video that I thought was kind of a nice illustration. I had to get one of these, except for I just got the video, so that's maybe even better. So right now there's an acceleration being experienced by the liquid, and that's why its surface is deformed the way it is. And along the bottom of that tank there is a pressure distribution that wouldn't exist if conditions were static. The pressure is higher on the outside edge of the tank and lower at the center bottom of the tank. And so the pressure is varying as a function of radius. Here, the axis of rotation is the center of the, whatever that is, a chair or something. Oh, slow motion. I didn't look at this part of the video. Oh, this is so much better. I don't know. This slow motion is sometimes just a gag, right? But there it is. All right. So we've seen some rotational flow. Here's how we can quantify centripetal acceleration in two different ways. One is if we know the velocity, the tangential velocity, meaning the velocity of some particle that is rotating in a circular way. V sub t would be the velocity of the end of a tip. So if it was, for example, like a propeller or an impeller that's pumping water. So the furthermost from the center of rotation, we could find the velocity there, square it, and divide it by r, which is the distance from the center to that point. And that gives us the radial acceleration. Or we can describe the velocity in angular terms. And you probably all remember that in one rotation there are 2 pi radians. And so if we're describing the angular velocity in terms of how many radians you're passing through per second, then you simply need to square that and multiply it by the radius. The units of acceleration are going to be meters per second. And so radians are kind of a non-unit in a way. If you look at what we're doing, we're squaring them and then multiplying it by a distance, meters. And so to get meters per second squared, we have to have the second squared come from the angular velocity, and the distance comes from radius. Now, a lot of the problems that you'll face, just because it's common to talk about pump speeds, for instance, in terms of RPM, you'll commonly have to convert between rotations per minute, or sometimes revolutions per minute is what it's called, RPM, to radians per second. And so if you keep in mind that there are 2 pi radians per revolution and 60 seconds per minute, what that means to go from RPM to radians per second, you simply multiply by 2 pi and then divide by 60. And that's how we can convert between the two. So here are some more pictures of rotational flow in both a liquid and in a gas. This is a tornado. You can make a little water vortex that's kind of interesting. Oh, commercial. We'll wait for it. Thank you. Yeah. So as the water drains out of the bottom, it provides enough energy for this rotational flow to set up. There it is. It was worth the wait. So unlike the previous example where they were rotating the aquarium with an external force, here the energy to cause that rotational flow is just that the liquid is draining through the bottom. All right. So just as an illustration of how we go through calculations, let's consider this device. Ironically enough, this is called a U-tube because it's U-shaped. You'll notice that this U-tube is open at both ends, which means the pressure of the air inside of the U-tube is atmospheric. And so what that tells us is that the pressure of the liquid at the interface between the gas and the liquid, the pressure here is also atmospheric. So since it's easy to do our calculations in gauge terms, we would say that the pressure is 0 at this location, and it's also 0 there. Now the little arrow gives you a clue. What would you guess that this symbol is saying? It's rotating, and also it's telling you the location of the axis of rotation. And so it's rotating about the left leg. You'll notice that here we've got the radius defined between the left leg and the right leg, and also the deflection is specified right now. Here's the equation for rotational flow. At first glance, it looks a little bit like Bernoulli's equation, except for the third term. We have a pressure head term, which is the same. We have an elevation head term, which is the same. But now this third term isn't the velocity head that we would see in Bernoulli's equation, but rather it's taking into account the rotational motion of the liquid. And so omega squared, where omega again is the rotational rate in radians per second, r is the distance away from the axis of rotation. And we can say that between 2 points, the sum of those 3 terms, actually I should be careful to point out that this is a minus here. So combining those 3 terms where we add the first 2 and subtract the third, there's conservation between 2 points. And it's always a good habit for us to pick our locations wisely, where we know as much information as possible for location 1 and location 2, so that we can either substitute in actual values into this equation or cancel terms out by virtue of, for instance, saying that location 1 is here on the left leg, location 2 is on the right leg. What would be the benefit of that, of saying here's 1 and here's 2? Pardon me? You can cancel things out, specifically the pressure term, because the pressure at both of those interfaces are the same. Also, by virtue of the dimensions that are given, we can say something about the elevation, z1 and z2. We could say, for example, let's have z1 be 0 and z2 be 0.25 meters. So we're on a good track so far. If this is location 1, here on the left leg at the interface between the gas and the liquid, if this is 1, then what's R1? 0, right, because it's right on the axis of rotation. All right, so really, we know everything that we need to know. We have R2 defined by this dimension at the bottom. And here in the example, I'm saying the first thing we'd like to calculate is find omega. What is the rotational rate in terms of radians per second that this thing is spinning? In other words, how fast does it have to spin for it to set up like this, for there to be a 25 centimeter deflection when you've got a 10 centimeter radius? All right, yes, go ahead and solve that, and let's see how quickly it has to spin. The next segment here, find the acceleration in the right leg and the tangential velocity in the right leg. Well, both of those can be found using this formula. So tangential velocity is going to be r times w, omega, r times omega, and then the centripetal acceleration will just be omega squared times r. All right, I went into full chicken scratch mode with this drawing, but the advantages of having a drawing at least is you're clear on which one I considered location 1 and where I considered location 2. Because unlike Euler's equation, where we had to be really careful about where is 1 and where is 2, here the directionality of that, it doesn't matter. You know, like in Euler's equation, we said location 2 was whatever had the most x or the most z, depending on the direction of acceleration. So the only reason why I want to keep track of where is 1 and where is 2 is because they're going to have a different radius and a different elevation. All right. So for the picture that I've drawn, now I just sort of identify what the variables are. The pressure at both locations is 0. Now, they're not exactly the same pressure, but air pressure doesn't change a lot through 25 centimeters. You know, the unit weight of air is 10 newtons per cubic meter. And so you have to go pretty high up into the atmosphere before you see reduction in pressure because of moving through a gas. It's different than a liquid. So to simplify, I'm going to assume that the pressures are equal, and I'll set my vertical datum at the water surface at 1, which makes Z2 0.25 meters. And so I'm just solving for the omega, and you'll see that when you go through and do that, it's 22.15 radians per second. And the units of that, if we look in here, we've got meters squared in the numerator, meters squared in the denominator, so that cancels out, and so it's just inverse seconds squared, and I take the square root, so it's just inverse seconds. And so the units here, it's 22.15 inverse seconds, which is the same as radians per second. Radians is this magical unit. It's there, it's not there. So, all right. Okay, the next part for B is find the radial acceleration experienced in the right leg. So, oh, by the way, it wasn't asked, but if it had been asked, then 22.15 radians per second, I could convert that to revolutions per minute by multiplying by 60 seconds per minute and dividing by 2 pi radians per revolution, and then that would get us into revolutions per minute. So it's the opposite of the conversion I showed you before, because the conversion I showed you before was to go from RPM into radians per second. All right, acceleration in the right leg, we just square omega, multiply it by the radius, so it's 49.05 meters per second squared. That's the acceleration that's being experienced there. and then the tangential velocity in the right leg. So any questions that came up in your mind as you worked through that example? What?
Why did radians just appear and disappear?
That's a great question. I don't know. I've never been curious enough to get to the bottom of that. But if any of you are, I'd be curious enough to have you tell me. So. Huh?
One radian is equal to where the radius of the circle is equal to the arc length.
Okay.
Meters over meters.
Meters over meters.
Or unit of length over unit of length.
Okay. Well, I'm glad that you know. Between all of us, we maybe have a working functional knowledge of fluid mechanics, right? All right. Okay. So here's another one, but this is enclosed. So this is a bit different than the other U-tube, because the other U-tube was open. That allowed the liquid level to vary. So here, since it's enclosed, the water elevations can't change, but the pressures still will. And so this is in some ways similar to Euler's equation, where sometimes we'd have an open container of liquid that was accelerating, and so the water was sloshing around because of that. Or it could be enclosed, and the water or whatever the liquid is can't deform its surface, but the pressures can still be different. Now this one's going to be a little bit different from the first one for another reason as well, and that is that it's not rotating about one of the legs. It's rotating somewhere in between the two legs. So the rotational rate here is defined in terms of RPM, which is revolutions per minute. And we know the pressure at L. We know the liquid is some sort of an oil with a specific gravity of 0.85. And so that means we're going to have to convert from a gamma of water into the gamma of oil using this specific gravity. And they're trying to find out the pressure at M at this location where we know the elevation difference is 12.5 centimeters. We know the R for both points. And this is just a matter of substitution and solving. Once you convert the revolutions per minute into radians per second.
How did you not get that answer? Alright, am I doing anything wrong here? I swear this is right. These pascals over this.
The pressure's wrong. Isn't it lower than that? It's only 2.75, so that's 2,750.
Oh my gosh.
Oh, and your unit weights too, right? It's not. Oh yeah, you've already got that. All right. Lots of number crunching on these ones. Because of that, I always do like these little secondary steps so that I can check my work and make sure that each piece is right as I do it a second time. And it's also kind of interesting to calculate each of these components separately because it's telling you the pressure changes due to certain facts about the situation. Like if you made the U-tube wider, then that would change the radius. You know, if you shifted the axis of rotation one direction or another. So you can kind of see the individual effects that each of the, for example, elevation difference, that effect that it has. And so the hydrostatic equation is built into this in the same way that the hydrostatic equation is automatically built into Euler's equation too. You know, this 1.25 multiplied by the unit weight, that's handling hydrostatic difference in pressure right there. And then these other components have to do with how far away they are from the central axis of rotation. All right. This is a before and an after at the same time. Before it rotates, here's where the water is, but then it starts to rotate at 8 radians per second at the location that's shown. And so obviously once it starts to rotate, then the water elevations aren't going to be there anymore because it's open to the atmosphere. We have to sometimes look very closely to see if it's enclosed or if it's open. This, even if it was capped, then the water levels would still change because it would just compress the gas on the right, and on the left the gas would decrease in pressure. But if it was capped right at the liquid surface, then that would be a different thing. So what I'd like you to do on this one is try and find out where, so far we've looked at changes in pressure and changes in elevation. Here we're going to try and find out what is the z that is resulting for a known rotational rate, and we've got the radiuses fixed. But let's say this, you're going to need one more relationship to be able to solve this because there's two unknowns. Z1 is going to be unknown and Z2 is going to be unknown, because where is the water going to be higher and where is it going to be lower? Just by looking at it. It's going to be higher on the right. How can you tell? That's right, because the axis is shifted to the left. That means the right leg's radius is larger, so it's experiencing more acceleration. And the elevation increases in the opposite direction of acceleration, just like how we would say that the pressure increases in the opposite direction of acceleration. So here, there's more acceleration in the right leg because it's further away. And so the water level is going to go up on the right and down on the left. So let me pose a hypothetical to you. What if the water level increased 1 centimeter on the right? What would happen in the left leg? It would decrease how much? The same, 1 centimeter. Because just by inspection, we're assuming that the diameter of this tube is constant everywhere. So if it goes up here, it comes down there. And so the little shortcut that I'm going to put in your mind to help you around the fact that there's two unknowns in this equation, in the rotational flow equation, we have to come up with one more equation that relates Z1 and Z2. We could use Z1 as a datum, except for it's going to be changing. And so I think there's an even simpler approach. If we just use the bottom leg as a datum, then what we could say is Z1 plus Z2 is equal to 0.36 meters. And then what we can do with that is write it in terms of Z1 is Z2, 0.36, 0.36 minus Z2. And so now, in this equation, if we make that substitution, there will just be one unknown. Because that's the total amount of water, and although we're changing the location of the water, we're not changing how much there is in the vertical part of it. So if it goes down 1 centimeter on the left, it goes up 1 centimeter on the right. The total distance of the two is going to always be the sum of what's there already. And so this is just another way of expressing that. The sum remains unchanged. Of course, we have to put an asterisk next to this, because if we spin that fast enough, what if the water's down to here, right? So what if Z2 is 0.36 and the water's down to here? And then we spin a little bit faster. Then what happens? Then you start to lose radius. Then the water level is down in the base. And so that is a possibility, like if your numbers are just crazy and you get like a negative value for Z, 1, like it's saying that the water is supposed to be down here, then that tells you that actually it's in the base. But for this 8 radians per second, it won't be. We'd need to spin it faster than that. So let me turn you loose on this one, where we're trying to solve for the elevations once it comes into equilibrium because of rotating at 8 radians per second. I don't think it should be. I think that there's just a single solution. Yeah, so if you go for the 14 radians per second, then the liquid is going to be down in the base leg. Yeah. All right, so here's the solution. Z1, which is the elevation in the left leg, is 0.0215 meters, and in the right leg, it's 0.3385. We don't have the time to actually go through these calculations, but if the rotation rate increases to 14 radians per second, then you should get a negative value for Z1, which means actually that now the water is down here in the base, and so now we're going to have to, the unknown becomes R1, because we don't know exactly what that radius is going to be, how far the water is from the axis of rotation. So we would need to put together a new formula that relates R1 and Z2, keeping in mind that the total amount of liquid is 18 plus 18 plus 18 plus 36. So that's the direction we'd go in if we had a little more time.
Well, what if instead you just did the same thing and used Z1 and substituted one value? I still got the negative.
Yeah, I don't think we could substitute directly into that, because the radius is going to be unknown. We don't, R1 isn't 0.18.
So it would be the same if you increase it from 8 to 14 rather than having it go from 0 to 14?
What do you mean, would it be the same?
Like, when it starts at 8 and goes to 14, it wouldn't be the same. That's at 0 before the
Yeah, that's at 0.
It would be the same going to...
The total amount of liquid would be the same. If you add up all of the distances, the total amount of liquid would be the same. Okay, that's all I have for you today.